Greetings. It is Monday, August 25. This is part two of the MSc 505 lecture. In the first part, I finished up chapter two of Callister talking about bonding, and now I'm beginning chapter three, which is a discussion of crystals. So bonding is local, mostly. There are, some exceptions. For example, metallic bonds will have an extended element due to the block wave, but mostly bonding is local. But these local bonds allow solidification into a solid. So how do we talk about this? Well, the discussion of this has to do with the order of the atoms locally, or I say the order of the atoms in this solid. Now, as an aside, this idea, let me change colors here. Order is essential for defining phases. And when you get into thermodynamics, you'll talk about order parameters, which are a direct measure of what phase is present. And this can come from diffraction or spectroscopy methods and others as well. But for here, we just want to talk about order as it pertains to solids. And when we talk about order in solids, we can talk about short range and long range ordering. Short range order, this really is, you know, first nearest neighbors. And long range is higher order. So we're talking two, three, four nearest neighbor bonds. Because when we talk about a crystal, we're talking about bonding that's occurring throughout the crystal. So let's draw a simple picture about this. Let's imagine we have atoms that are going to be make green atoms here. And this looks a lot like a crystal, right? Well, it is a 2D crystal. And if I have this, I can pick some site. And I can say, well, that's a distance, and that's a short range order. It's the nearest neighbor. And it seems that, well, if I pick another atom, that's the same. Pick another atom, that's the same. So I have short range order. But I can also, for example, pick something like that, right? That's a one, two, that's a third nearest neighbor type interaction. And I can see the same thing here. I can see the same here, 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 here. I have these long range orders. And I can even go to further. I can pick a distance like you know, here. And I move this. I still have that. And I have something that looks like that. So I have these long range ordering that you can see. Now, let's go to something that has short range, but no long range. Let's pick, and I'm going to make a little molecule that looks like, well, I'm going to pick a molecule that looks like this, right? And I can have these molecules, and these molecules can be around each other. So this is some type of, I don't know, gas or fluid. And in these, I have a series of short range orders that are all the same. But if I start asking about long range, well, I've got something here, and then over here, well, I don't really have that. Uh, yeah, I guess I kind of do here, but that's really weak compared to what we're observing on the left-hand side. Same thing. If I go to even longer range, let's say I've got something that sits here. Is there another one that looks just like that? It's like, well, no, not really. So here we have, and here we have short only. So if we have a structure, we have a solid that has short range only, we call this an amorphous structure. And these are common engineering materials, glasses, polymers, a lot in biomaterials. And there's a lot of really unique properties about amorphous materials that make them great for engineering because you can control the chemistry. You don't have to worry about long range ordering. Uh, the processing allows you to control the densities and the local structures. So amorphous materials are really a significant part of materials engineering. But here we're going to discuss crystals. So Callister, chapter 3 is crystals, long and short order. So let's discuss crystals and how do we talk about these? So what makes a crystal? How do we define a crystal? Well, a crystal is made of two quantities. One is made of a lattice, and two, an atomic basis. And you need both of these to have a crystal, and you need to quantitatively define these to define the structure. So let's first discuss lattices. Well, before I do that, I should probably give you this picture of what I mean by a lattice and a basis. So this idea of a lattice, the lattice is it's basically an invisible box that's periodically spanning space, and then you put your atomic bases in the box. VASI. And then the atomic basis sits inside each box. So, for example, say I have some set of boxes. Now I'm going to define this box as one unit cell. And within that unit cell, I'm going to put an atomic basis. And, for here, let's just call it, I'm going to make it star, circle, star. Star, circle, atoms. So now this atomic basis is going to sit in every single one of these. And I should draw here, dot, 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 because our periodic lattice goes off to infinity in all directions. So mathematically, what this does for us is it says, oh, if you can define one unit cell, so you have one unit cell, and then you can define how that unit cell goes off to infinity, then you're able to describe this entire infinite size crystal. So how do we define the unit cell? How do we define this lattice? So let me draw a 3D unit cell. This is a unit cell. We're going to define this in terms of a set of lattice parameters. So we have a lattice parameter that defines the length of this side, the lattice parameter that defines the length of this side, B, and a lattice parameter that defines the length of this side. And then within this cell, we have angles. So the angle between the C and B, called the alpha angle, the angle between the A and C is beta, and the angle between A and B is gamma. So alpha, beta, gamma. And that's how we do it. Now, as an aside, those of you that perhaps are going to spend a significant portion of your life looking at crystals, instead of thinking about lattice parameters, it's better to talk about this in terms of vectors. So at least when I talk about crystals in research and I think about them, I think in terms of vector A1, vector A2, and vector A3. Vectors are great. Vectors are your friend. Vectors make math so much easier. But for this course, we're not going to discuss it. I'm just kind of pointing this out for those of you that may be encountering this in your research. So, how many ways can we how many ways can we make a unit cell? Well, the unit cells they have to complete space and they have to span space, right? You can't have unit cells that stack together and you have little regions of volume that aren't defined. And they have to be able to span space out to infinity. And we have friends over in math that work with us and tell us that there are 7 crystal systems and only 7 crystal systems. Well, for those of us living in three-dimensional space, there's only 3 crystal systems. Or sorry, only 7 crystal systems. So let's look at those. One, we have a cubic system. In the cubic system, A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degrees. A cube. Great. We can have a hexagonal, and that is A is equal to B is not equal to C, and you have alpha equals beta equals 90, gamma equals, so 90, 120 degrees. 3, we can have the rhombohedral, unit cell, and some people call this trigonal. I don't know the history behind that, but it's worth knowing that there are sometimes 2 names. I should look that up at some point to see why these two are different. But in the case of the rhombohedral, A equals B equals C, alpha equals beta equals gamma, and these are not equal to 90 degrees. And we have the orthorhombic, ORTHORHO, orthorhombic. In the orthorhombic, A is not equal to B is not equal to C, but alpha equals beta equals gamma is equal to 90 degrees. You have monoclinic. In the monoclinic, A is not equal to B is not equal to C. Alpha equals gamma equals 90, which is not equal to beta. 6, we had the tetragonal. I kind of went out of order here. In which A equals B is not equal to C, alpha equals beta equals gamma equals 90 degrees, and 7, we have triclinic, in which A is not equal to B, is not equal to C, alpha is not equal to beta, is not equal to gamma, is not equal to 90. So let me check that I got this right. Made at least one ordering error. And okay, yep, I got that right. So these are the 7 crystal systems, and there's only 7 crystal systems in three-dimensional space. Now, excuse me. The next question becomes, how do we decorate this lattice? How do we put the atomic basis in? And we do that by defining a lattice point, which is a fixed place in the lattice, and then we define our atomic basis relative to this point. So we have, say, some lattice point, and then we have some R1, and call this a star atom, and some R2, call it a square atom, and R2. So to draw that out and thoroughly belabor the point, ha, try that again. If I put my lattice point in the center, and it doesn't have to be in the center, it's actually more common for us to define our lattice points at the intersection, but I drew it at the center. Now I've got a R1 and a R2. So at each point, I now have dot, 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 because this, again, goes off to infinity. So this is how we do this. Now, most commonly, and not all the time, but it's not uncommon. Uh, you have only one atom. Frequently, one atom basis, and we'll simply say R is equal to 0, 0, 0. And as a result, you're basically defining a single atom that sits at the vertex of the lattice. And that's a handy way to do it. Now, the next question, which I'm going to leave until the next lecture, is how many ways can we put lattice points in our 7 crystal systems? And I will go into this in the next lecture. For now, what I want to point out is that I sent out a homework set that I'd like you to turn in next Monday, and I will be putting together another homework set that covers more from chapter 3. If you have any questions or comments, please do write, and I would certainly be happy to talk with you or arrange a time to meet. So thank you very much and have a great rest of your day.